Recording starting now. Okay, so our problem is that a car starts from a standing start, accelerates steadily to 60 kilometers per hour over a 2-minute period. And the question is, how far does it travel in the first minute? And we had 4 options. Okay, so just to think about this, so if you believe the ideas that we developed yesterday, they should say that basically, if you want to know the answer to this question, and what you know about is the speed of the car at any given time during the period that you're interested in, which is 1 minute from a standing start, then you should look at the area under the graph of the car's speed against time. So there's a couple of there's a couple of slightly complicating factors here that weren't in yesterday's examples, which I picked for myself to make my own life easy. But one is that the speed is given to us in kilometers per hour, but the time is given to us in minutes. So we should sort of adjust the units so that they're compatible with each other. So if we measure time in minutes, we're interested in the first minute, and we're interested in the 2-minute period in total. So we start at 0 minutes. The information that we have goes up to 2 minutes, but we only care about the first minute. And what we know is that our car accelerates steadily over the 2-minute period. So the graph of the speed against time should look like a straight line, sort of an increasing straight line, something like that. At the end of the 2 minutes, we're at 60 kilometers per hour. So at the end of the first minute, since the acceleration is steady, we're at 30 kilometers per hour. But our speed is given to us in kilometers per hour, and we care about time measured in minutes. So just to kind of allow for that, we need to adjust the units in which speed is measured so that they correspond to how we're measuring time. So whether you change the time to hours or the speed to minutes doesn't really matter, but I'm going to change the speed to minutes. So here, after 1 minute, we're at 30 kilometers per hour. But 30 kilometers per hour, an hour is 60 minutes. So if you're doing 30 kilometers per hour, you do a kilometer in 2 minutes. So you do half a kilometer in a minute. This is not a very standard measure of speed. But 30 kilometers per hour is half a kilometer per minute, and 60 kilometers per hour is, of course, 1 kilometer per minute. So if we care about the distance traveled in the first minute, and if you believe all the arguments that we developed yesterday in our first lecture, then what you care about should be the area of this triangle, which is enclosed under the speed graph over the first minute. And that triangle is basically 1 minute in width. So it should be, the area of it should be 1/2. Oops. Times the length of a space, which is 1 minute, times its height, which is half a kilometer per minute. So in fact, it should be 1/4 of a kilometer, or 250 meters, which was actually the least popular of the 4 answers, as it happens. But it doesn't really matter. It was a straw poll over a couple of minutes. So yeah, but that's the idea. And I suppose our business in this course isn't really to calculate distance traveled by cars, but it's an example of something that's captured by the area under a curve, which is really the relevant point. The thing that made this question slightly tricky, as well as the fact that I asked you to solve it in 2 minutes with no warning, was just the fact that it was there was this sort of adjustment to be made about the units at which the speed and the distance were measured. So hopefully that makes sense. And if nothing else, it should hopefully serve as a sort of recollection of where we were yesterday. So if anyone has a question, please feel free to throw it into the chat or to turn on the microphone. Okay, if not, that's where we're at. And we're just going to pick this up now and sort of look in a bit more detail at this general problem. So we can forget about cars traveling now that we're sort of done with that for the moment. And we're going to look instead at some related ideas, of which this might be sort of the first example. Okay. So can you see now a slide entitled A Harder Problem, but more realistic? If not, just throw a comment into the chat. Okay, so this is where we were yesterday. We looked at that example. Okay, so here's another question, and we're not going to answer this one right now. But basically, so the examples we've had so far have been sort of deliberately chosen so that we're able to calculate the areas involved, because they're essentially just triangles or combinations of rectangles and triangles. So if the speed function was something more complicated, so for example, here's an example. So again, our car is traveling for 1 minute. This time its speed increases from 10 meters per second to 20 meters per second again over the 1 minute, but according to a different formula, not a steady adjustment in acceleration, but a formula given by this quadratic function of time. Okay, so we can observe that if we put t equals 0 in here, we get 20 minus 3,600 over 360, so we get 10. And that if we put t equals 60 in here, then the second term falls away and we just get 20. So certainly this is a case where the speed changes continuously from 10 to 20 meters per second over the 1 minute period, where time is measured in seconds. So fine, that could happen. We can observe that the function v of t here is a quadratic function of t, so its graph is a parabola. Fine. And our question is the same. How would we compute the distance traveled in this case? Okay, and in this case, the picture is like this. That's a graph of the function, this quadratic function over the time from 0 to 60. So it's obviously a piece of a parabola because it's a quadratic function. And the basic principles should be the same. Again, we can do what we did yesterday. We can split this area into a bunch of rectangles. We can argue that the distance traveled should be the area shaded in red there. But we don't have a way of calculating it because it's not just a combination of triangles and rectangles. So this example, we're not going to do anything more with it right now. We're just going to kind of observe that for this case, the argument works just in the same way. We can use the exact same sort of concept of splitting the area into a bunch of narrow rectangles and taking the limit of that process as the width of the rectangles goes to 0 and the number of them goes to infinity, and say that the answer to this question should be the area under the curve. But how are we going to calculate it? So, what we need really, if we want to be able to answer questions like this in general, is some kind of theory or method that would allow us to calculate the area in a picture like that, bounded by a section of a graph defined over some specified interval from 0 to 60 or whatever, and with its upper boundary defined as the graph of some function for which we might have a formula, for which we don't have at the moment a method for computing this area. So I suppose the point of all this really is, this is a continuation of yesterday's introduction, is that there are cases where we might want to be able to do such a thing. And we might want to be able to have a method for solving exactly that problem, where we know the function whose graph is in question, and for some physical reason, maybe arising from some application like this distance traveled thing, we have some reason to want to know the area under the graph. Okay, so we're supposed to be doing calculus, and you've studied a lot of calculus already, and you know all about differential calculus, and so hopefully there's some sort of connection to that if this is still calculus, and that's really our next step to get at what that connection is. Okay, so just a comment, and this is something you can look at later. I'm not sure if all of these examples are sort of totally convincing, but the assertion is this example of something traveling and knowing about its speed is not the only case where it's relevant to be able to calculate distances areas under graphs like this. So for example, you could be looking at a solar panel, and you could have some record of how the light intensity, which is hitting the solar panel, is changing over time. And that's something, again, that's varying continuously in time. So it's not that it's constant for a period of time and then jumps to another constant value and stays there. It varies continuously. So again, the total energy stored maybe can be modeled as the area under some kind of graph that measures the light intensity against time, which is, again, a continuously varying thing. And the idea is the same. You want to sort of add it up over the whole day, but the variation is continuous. So it's not quite an addition problem. Other examples, and this third one is one that I quite like, although it's kind of a purely mathematical one maybe, but it also could arise in applications. If you want to calculate the volume of some sort of object, like think about the formula, for example, for the volume of a sphere. So you could imagine that by taking your sphere or a cone or whatever it is, and setting it down on a table and taking sort of horizontal cross sections of it. And you could approximate the horizontal cross sections as cylinders of some thickness. Let's say that your sphere has a height of 10 centimeters or something, and you divide it into 10 horizontal slices. And imagine each of those to be a cylinder. whose volume you can compute because it's just the area multiplied by the height. And that gives you an approximation to the volume of the sphere. And if you take finer and finer slices, your approximation should improve. And the limit of that process is kind of taking slices of thickness 0, but having infinitely many of them, which again can be modeled as the area under some kind of graph of a function whose value at a given height above the table is the cross-sectional area of the sphere at that value. And from that, you can develop a formula for the volume of your sphere or cone or whatever it is as the area under some graph. So there's lots of examples where this kind of idea arises, where you want to sort of add up something that's accumulating continuously and get a total value for it. But it's not adding up a finite number of things. It's kind of it's sort of trying to calculate a total of something that's accumulating continuously. The concept arises quite often as well in probability theory and obviously in its applications in statistics, where, for example, if you want to know the probability that if you choose a random person from the population, that their age, let's say, is between 20 and 30 years, then that probability is given by the area under the graph of some appropriate so-called probability density function over the relevant interval, which would be from 20 to 30 years. So this idea is a useful one. I guess that's what I'm trying to kind of convey and trying to get at, and one which arises quite often in physical applications and in other applications to areas of study that are of interest. Okay, so those are just some examples. And again, we're not really going to go into these examples in detail. It's only to give sort of, I'm just trying to give an impression that this is not something that's it's purely of theoretical interest. Okay, that's the end of the first section of the lecture notes. And so what I kind of hope you might take away from this section would be, an idea of why it's of interest to be able to calculate the area under the graph of some function over some specified time interval. And secondly, maybe to explain how such an area can be approximated using rectangles, using these sort of vertical columns that we talked about yesterday. And so, the examples that we used were were motivated by some story about a car moving, but the same principle applies to any context at all, where you've got the graph of a function. Okay, and if you could evaluate the function at points along the interval, then you can model the area that it encloses by these sort of narrow columns, narrow rectangular columns, whose width and height and then you can take some sort of limit of that process as the width of the columns goes to 0, and this is the concept of a so-called Riemann sum. And then I suppose the third thing is there'll be a few of these in the first homework sheet, is just to solve some simple problems, like those examples where we had a car moving and the acceleration was steady, so that the area could be conceptualized just as a combination of rectangles and triangles. So that's it for section 1.1, really. We haven't, I suppose, really kind of get out the definition yet of the things we want to talk about, which are integrals, but that's what's coming up next. So does anybody have a question at the moment before we proceed to the next section? Okay, perfect. So thanks everyone. So I'm going to stop sharing that one and move on to the next section. So again, this section is sort of setting us up really for next week's content, which will be learning some new techniques. Okay. Okay, so if you can't see a set of slides that starts with section 1.2, the definite integral, please complain loudly. Okay, so this is a short section. And basically what it's about is learning a little bit of kind of language and notation that goes along with this subject of integration. So we're going to talk about something called the definite integral. And ultimately, we're going to be calculating definite integrals. Sorry, I have some kind of minor problem here. 1 second. Okay, so the goal of this section basically is to learn some terminology and notation for describing these so-called definite integrals. So a definite integral is exactly the thing that we've been talking about so far: the area under some graph defined by some function over some interval. So the lingo for that is a definite integral. And the reason why this is called a definite integral and not just an integral is something that we'll meet shortly when we come to the indefinite integrals. Okay, so we sort of noted last time that we'd like to have a method for calculating or at least discussing these areas enclosed between graphs. So such a method does exist, and it forms part of, but not all of, what they call integral calculus. So we need a bit of technical language and notation for talking about areas under curves. So really the goal of this section 1.2 is just to introduce that language and notation, some words of the subject that we need to have in our vocabulary and some notation. And I suppose the reason why I'm making this into a special section is because the notation is a bit obscure at first glance, and it's not really obvious why it is developed the way that it is. So, okay, so forget about cars, traveling, etc. We're going to abandon these applications for a while and just think about functions, which are the basic objects, I suppose, of calculus. So here's an example. Suppose we give ourselves the function, which is defined by f of x equal to x squared. And we can observe, the relevance of this maybe is not obvious yet, but it will be shortly, that function is positive. Its values are positive, actually everywhere except 0, but in particular in the region between 1 and 3 on the x-axis. So in the region between the vertical lines 1 and 3, x equals 1 and x equals 3, we can draw a picture of the setup. Here's 1, here's 3, here's 0. And the graph of y equals x squared, of course, is a parabola which passes through the origin, and it has the basic shape, sort of like this. Okay, this is not going to be a great picture, but maybe it's plausible enough. So this is the curve y equals x squared, which is the graph y equals f of x. Okay, that's what our picture looks like. And if we say, it's a terrible picture, but if we say that we are interested in the region between x equals 1 and x equals 3, so x equals 1 is the vertical line through 1 on the horizontal axis, x equals 3 is the vertical line through 3, and sure enough, the graph of the function is sitting up above the x-axis in that region. And supposing that we cared for some reason about the area of that region that's enclosed between the vertical lines x equals 1 and x equals 3, under the graph y equals f of x, y equals x squared, and above the horizontal axis. So that's the area that's shaded here in blue. Okay, and of course, I suppose the first section of the notes was supposed to persuade us that there are indeed reasons why we might be interested in such a thing. So it's this area. Okay, so the area of that region is some positive real number. We don't necessarily have a way of calculating this, but we might have reasons to want to know what it is, coming from some problems like the ones we just talked about. What we want to talk about in this section is not really what the area actually is, but how we denote it. So that area, the area of that region, which is a number, is called the definite integral of x squared, which is the function defining whose graph we're interested in, from x equals 1 to x equals 3, which are the left and right hand endpoints of the region. And the way it's written is like this. Okay, so in case these symbols are not immediately familiar to you, we're going to be dealing with them quite a lot in the next few weeks. So this gadget, this thing that looks like an F without the horizontal dash, is called the integral sign. The 1 and the 3, obviously written at the subscript and superscripts on that, are the left and right hand endpoints of our interval. This is 1, that's 3. The x squared is the function, the expression whose graph defines the upper boundary of the region. And the dx is kind of stuck on there as a little tag, and it's the same dx that you see in dy dx when you're talking about differential calculus. And the reasons why this thing is written that way, I think, are really not at all obvious. It's a classical piece of notation, I guess, that has sort of evolved throughout history since the concept of an integral was invented. And it's not the most, it might not be the notation that you would make up if you were inventing notation for this gadget. So I suppose what I want to do in this section is just, introduce this notation, make sure that we're able to use it, and try to give an explanation of where it comes from, because to me, I have to confess, it looks like a fairly obscure thing that is probably not what any of us would come up with if we were asked to invent some notation for this concept. Okay, so that's where we are. So this thing, I suppose the words that we should give our attention to here are definite integral. This is the definite integral of x squared from 1 to 3. And I suppose, if I see this thing written in text somewhere, the words that go through my mind if I'm reading it are the definite integral of x squared from 1 to 3. Okay, maybe not completely consciously or overtly, but that's how I read it. Okay, so in general, for a function f and numbers a and b, this thing is typically a number if it's a thing that can be calculated at all. And the question of how you calculate it is not what we're addressing in this particular section. Okay, so just to labor that point some more. So if a and b are fixed real numbers with a less than b, so a, again, when you see a less than b here, think of that as saying that a is to the left of b on the number line, and let f be a function for which it makes sense to talk about the area enclosed between the graph of f and the x-axis over the interval from a to b. So that's a slightly vague statement, but what it means is basically that the graph of f is something that's either continuous or at least has only a finite number of discontinuities if it's not continuous, that is defined more or less everywhere on the interval from a to b, and that it doesn't fly off to infinity, so that it doesn't, so this area is not something that's infinite. Okay, so for example, when I say it makes sense to talk about this area, if you had a function f that was completely discontinuous everywhere, so that its graph was just a bunch of dots scattered in a completely haphazard way, that would not be an example of something for which it makes sense to talk about this area. Okay, so basically, all kind of reasonable functions in the world of calculus are admissible here. Okay, so the definite integral from a to b of f, denoted this way, is defined to be, okay, so this is how it's defined in general, and we'll come back to this one as well. So in general, if your pictures like this, you have an a and a b. Okay, and the a and the b are the limits of the region that you care about. So think of those as specifying vertical lines, which are the left and right hand endpoints of the area that you care about. The graph of f maybe looks something like this. Let's just say that f is continuous. It doesn't actually have to be continuous. It could have a couple of discontinuities, like it could have a couple of jumps, like those first examples that we looked at yesterday. So, even if f had a jump discontinuity somewhere, it doesn't really change the possibility of talking about the area, so that's okay. So, okay, so if that's the graph of f, then what we mean by that definite integral from a to b of f is essentially the area enclosed between the graph of f and the x-axis in the region with the left and right hand endpoints that are specified, with one small adjustment that didn't arise in the first example, which is that if the value of f is negative anywhere in the region, then those parts, I'll change the color there, then those parts of the region that are below the x-axis that correspond to negative values of x are regarded as negative. So what the definite integral from a to b of f of x would be in this case would be not exactly all the area of that region between the graph and the x-axis, but that with the proviso that area that sits above the x-axis is considered to be positive. That's supposed to be a plus sign. And area that lies below the x-axis is considered to be negative. So for example, if the area above and below the x-axis happened to be exactly the same, then the definite integral would be 0, because the positive and negative parts of it would just cancel each other exactly, and that's something that can happen. So the example there that we had in the previous slide of x squared was kind of an easy one because of the fact that it's sat completely above the x-axis. So the definite integral was just the area. In general, this is just a point to note, really, for to be aware of later. In general, what that definite integral is basically all the area, except that the area colored in yellow there, sitting below the x-axis, is sort of counted negatively. And so you can have a cancellation between the positive and negative parts. And it can indeed be true that the value of this definite integral can be a negative number if the area sitting below the x-axis exceeds the area above the x-axis. Okay, so the definite integral is basically this concept of the area enclosed between the graph and the x-axis in the relevant interval, with the proviso that area below the x-axis is counted negatively. Okay, so I suppose the point here is just really to be able to kind of recognize this notation. We're going to be using it quite a lot, and we need to have a sort of a fairly good concept of what it means. So, a few remarks. Oh yeah, first I think I've said that already, is, this comment that it makes sense to talk about the area enclosed between the graph and the x-axis is basically that the function is sort of a reasonable thing, not something whose graph is a bunch of completely scattered points, for example. So if you had something like this, let's say your left and right hand endpoints were here and here, your function could be something like that. It could have a discontinuity here, let's say. It could look like that, for instance. That's fine, because in that case, the area enclosed between that graph and the x-axis is okay. It is something that makes sense. That function is not differentiable everywhere. Like I say, it has a couple of discontinuities. It's not continuous everywhere either. But it is what they call integrable, because it still makes sense to talk about the area that's enclosed between its graph and the x-axis. But if you have a function which has discontinuities all over the place, like everywhere, and its graph is literally just a bunch of points, then you can't really talk about the area that it encloses between its graph and the x-axis. So something like this is okay. But something whose graph doesn't even have some sort of continuous parts is not okay. Anyway, that's not something that we have to worry about too much. It's just to note, I suppose, that there is a concept of integrable functions that captures these concepts very precisely. Okay, second thing, this is really what I wanted to mention about this notation. So in my opinion, this notation is a bit, what's the word? It's not the easiest thing to kind of make friends with, because it's a bit chunky, it's a bit obscure. So this is just a note in case it helps to kind of explain the various kind of ingredients in this expression, in this written expression for the definite integral from a to b of a function f. So this gadget, this kind of thing that looks like an f, is the integral sign. That's what it's called. It's not something, I don't think it's used in any other context, at least in communication in written English, apart from the integral sign. And so the dx here, whenever you see an integral sign, it'll always have a dx or a dy or a d something accompanying it. And so the integral sign sort of opens up the expression like a left parenthesis or a left bracket, and the dx kind of closes it. So the integral sign and the dx go together. The integral sign on the left and the dx on the right. So the dx kind of indicates to us that f is a function of the variable x, and that we're talking about the area between the graph of f of x and the x-axis. So basically, x is the variable with respect to which the function is written. And that can be important occasionally in cases where there's sort of more than one variable around. And you might need to actually sort of specify which one you're considering. You could have a function f that's a function of a variable y, and then y itself might be a function of t. And in that case, you sort of care about whether you're considering f as a function of y or a function of t, and which one you're integrating over. So that the dx generally is just kind of, you can sort of almost not pay much attention to it if there's no ambiguity, but occasionally it's important to note what variable it refers to. Okay, so the f of x part is called the integrand. That's a word that we rarely use, but in case you encounter it anywhere, it's that's how it's referred to. It's a function whose graph defines the upper or lower boundary of the region whose area is of interest. Okay, and then the numbers a and b. So here again is what we're talking about, the integral from a to b, f of x dx. So the numbers a and b, which will typically be, there'll be numbers, values on the real number line. A is usually less than b, but it doesn't have to be, but typically it is. So the numbers a and b, which appear below and above the integral sign, are called the lower and upper, or left and right limits of integration. And they determine the left and right boundaries of the region whose area we care about. Okay, and in this expression, it is generally understood that a and b are values of the x that appears in the dx. If there's any danger of ambiguity there, you can write it this way if you want to, and sometimes it can be useful. We'll see examples like that. So another remark about this is this use of the word limit is completely unrelated to its other uses in calculus, like where you're calculating limits of functions as the variable approaches some value or approaches infinity. So these are the limits of integration. So it's a good thing to have the word limit in your vocabulary in this context, but try to avoid the risk of confusing it with other uses of the word limit in calculus, of which, as we know, there are plenty. So, okay, so that's the various bits. So I suppose I don't know if you share this view, but I feel this notation is so obscure that, some kind of explanation of where it comes from might be warranted. So this is not terribly important from our syllabus point of view, but just to kind of say where it comes from, and maybe it helps to kind of make sense of how it's used as well. So this notation was introduced by Leibniz, kind of in the second half of the 17th century, and it has kind of evolved. It has come to us more or less in the same form that he used it. And the rationale for it was, and is, sort of like this. So the areas were estimated much as we did with the examples in the first section. Sorry, that should be section 1.1, not section 3.1. And so the interval from A to B, over which you care about this area, would be divided into narrow subintervals, and each of them would have a width which would be described by this delta x, which is again something that's used in differential calculus as well, to describe like a small interval of variation in x. And so the expression for the estimate of the area would have been something like this. It would have been something like a sum over some I of areas of rectangles whose width would have been given by delta x. That would have been the width of the narrow rectangles, and the height of each of them would be something like the value of f at xi. So it would be a sum over I, and the picture would be something like this. You know, you'd have your picture like this. A and B would be here. You'd split the region into a bunch of subregions. X0 maybe would be the left-hand endpoint of the first one, then x1 and so on. And the width of each subregion would be delta x. And so, for example, the height of the second little rectangle would be the value of the function at its left-hand endpoint. So the coordinates at this point here would be x1 and the value of f at x1. And so the area of that particular rectangle would be delta x multiplied by the value of f at x1. And the estimate for the total area would be a sum of things like that. So it would be written this way. Okay, and so Leibniz's sort of theory that was developed was basically you wanted to take a limit of this thing as the delta x would go to 0 and the number of the little xi's would go to infinity. And so the dx, which appears now in the integral notation, fx dx, from A to B, the dx was basically introduced as a limit of this delta x expression as delta x would go to 0. So notationally, it was just sort of, you know, inserted there as a sort of to capture this idea. This is the limit of delta x, so it's written as dx in the limit. And also the integral sign, which appears here, kind of corresponds to the summation sign that appears here. And it was taken to be a sort of limit of the summation sign as the number of things you're summing over goes to infinity. So the integral sign and the dx, you know, their origin, I suppose, is not totally obscure, even though they look sort of a bit strange now. The integral sign was introduced as a limit of the sum sign as the number of things you were adding together went to infinity. And the dx was introduced as a limit of the delta x, which was the actual width of a sort of genuine subinterval. So I don't know if that helps to make sense of the notation, just to have that little bit of context. It helps me a bit, but so maybe if it helps you, you might find it interesting. So that's how it was written. The total area would be approximated like that. This is a more legible version than my scribbles on the last slide. So the total area would be written this way, and the dx was sort of introduced as an expression to replace delta x in the limit. The integral sign as a limit version of the summation sign. So the integral symbol itself it's based on something that was called, I don't know much about typography, some of you might, but it's based on something called the long S character, which was in use in English typography until about 1800. It's fallen out of use now, except in this particular context of integral calculus. But you know, it's not something that was completely invented out of the blue. It was actually a character in typography, in written text. So now it still is, but only in this context of integral calculus. So if you're interested in the history of this, there's just a link that you might be interested in. There's a really nice, extremely detailed and extensive archive of history of mathematics there, and it's hosted in St Andrews University in Scotland, the Mac Tutor site. So in case you're looking for general sources of interesting mathematical information, that's a nice place to look. Okay, so that is essentially section 1.2. It's a bunch of notation. So I suppose at this point where we are, you know, I don't necessarily expect you to study that section in detail and kind of memorize everything. It's there really as a point of reference for when we're looking at further examples and you want to maybe make sense of the integral notation. So the learning outcome for section 1.2 is just to be able to use that notation for definite integrals accurately. It's, you know, I think the notation's a little bit obscure, so it does warrant giving it a little bit of attention to get used to it. One thing just to finish off today, we have a couple of minutes, is just a preview of next week, really. So that example that we started with in this section, I've been talking a lot about sort of the theory and the way we write things, and not so much about how we can actually calculate these values. So just to finish off today, just to note, and we're going to talk about this next week. So today I'm going to just give an example, back to that first example. So the first example that we looked at today was the definite integral from 1 to 3 of x squared dx. Okay, and the picture that accompanies that, of course, is we have the graph of x squared. It's a parabola. It touches the x-axis at 0. 0. 1 is here, 3 is here. That is really not a good picture. We'll compress it a bit, put 3 here. So the area that we're talking about is this area. Okay, and so the assertion is that we actually can calculate this. But in order to sort of see how this works, we have to talk about the fundamental theorem of calculus, which is the next kind of highlight of this section. But if we forget about the theoretical justification at the moment and just talk about how it's actually done. So to calculate this area, so the amazing thing is that you can actually do it. We have all the knowledge that we need to do it. The link between what we're about to do and the area interpretation is the fundamental theorem of calculus, which is our next main topic. So to calculate this, the sort of instructions are, find something, an expression involving x, whose derivative is x squared. Okay, so that's what this has to do with differential calculus. If you have, if you're not seeing that, you're not supposed to be able to see it at this point. It's something that's quite a remarkable connection between this area problem and all the calculus that you've studied so far. So why this would have anything to do with derivatives, not clear, but let's do it anyway. So okay, so we have to find something whose derivative is x squared. Well, we have to ask ourselves there, what do I have to differentiate to get x squared? Okay, we know how derivatives behave for polynomials. So the answer to that is basically x cubed, but x cubed is not quite right. Because if we differentiate x cubed, we don't get x squared, we get 3 times x squared. So that's like wrong by a factor of 3. But if we differentiate x cubed over 3, we get 3x squared over 3, which is x squared. Okay, fine. We can say that. Okay, so find something whose derivative is x squared. That's the first step. So x cubed over 3, there's an answer to that. It's not the only answer, but it's an answer. And then the next step is plug in the values at 3 and at 1. And subtract. So our expression whose derivative is x squared is x cubed over 3. Subtract the value of this thing at 1 from the value at 3. And if we do that, we will get 3 cubed minus 1. 3 cubed over 3 minus 1 cubed over 3. So that's 27 over 3 minus 1 over 3, so it's 26 over 3. And the claim is that the area of that region that's shaded in blue is 26 over 3. So, and that this is a sort of general method that can be applied to calculate these kinds of areas. Basically, find something whose derivative is the integrand in this expression, the x squared in this example. Okay, that's the hard part, because sometimes that's easy. In this case, it's not so bad. Other times it's difficult or impossible. But if you can do it, then you can actually calculate the values of these definite integrals by just basically plugging the 2 limits of integration, the 3 and the 1 here, into that expression and subtracting the value at the left-hand endpoint from the value at the right-hand endpoint. Okay, so I guess the point of this example is not, it's not that I expect you to sort of believe the justification for this method, but just to observe how it is actually done, and we will justify it in the next couple of lectures. So this is the area that we're looking for. The integral from 1 to 3 of x squared dx, the value of that thing is actually 26 over 3. So there's no strong reason at this stage, no compelling reason to believe that the area of that region should be 26 over 3, but that's how So one of our topics in the next couple of weeks would be to devise methods of finding expressions whose derivative is some specified expression. Okay, anybody have a question or a comment about any of that? I'm going to stop the recording at this point in case anybody wants to ask anything but doesn't necessarily want to record it. So thanks everyone. I'll stop the recording now.